Can I hear some approval to go?
Yes, please go ahead.
Please.
Yes, Doctor.
تفضل الدكتور.
شكرا جزيلا شكرا. We talked about the graphical tools in the analyze phase, but graphical tools are only starting point for the data door. So so all the theories that we gained from the graphical tools, we need to investigate them more using advanced statistical tools. Sometimes things show that it is probably going in a direction, but looking for a statistical evidence is probably more appropriate for so we'll look at the data door. And okay. So when you take the data, an important thing, and this is like a foundation block, is the histogram. You want to plot your data, and we talked about histogram before. But what you do, let's say you're taking age, for example. You take the age, and this is how you draw a histogram. So people who are from 20 to 30, age 20 to 30, we have 2 of them. 30 to 40. We have 4 of them, 40 to 50, another 4, and 50 to 60, and so on. This is the data. This is called a histogram or a frequency plot. And the frequency plot, a histogram, as we said in the data words before, a histogram is like the foundation block for all probability and statistics. So it's very, very important. But this is what a histogram is. Basically, you're taking ranges, and for each range, you're plotting the frequency of that range. So here we have 2 for 20 to 30, 2, 4, and so on and so forth. This is a similar one, but it's called dot plots. It's similar. It's just instead of a height with a rectangle, here you're putting dots, and it gives you. This is the minutes to eat breakfast. How much minutes? It's this is from 0 to 1. This many from 1, and so on. It's just this is how you do histogram. Moving from histogram to probability plots. The same histogram, as you can see, this is a histogram. From the histogram, you draw the best fit of the histogram. You get a probability plot here. So basically, this is the probability that you will find if it's the age at this point. This is the probability that you'll find it at this point. And normally, we're talking about ranges. The cumulative plot basically is the integration around. It's just basically the area below certain things. So this is the same thing, it's just how much area. By this time here, you're getting this much area. By this time, you're getting this much area. And it's nothing but it's actually the integration. So this is called the probability plot. And the purpose of the probability plot here is to tell you if your curve here that you fitted on the data, is it normal or is it not normal? If it's normal, that means it's a straight line. And the importance of this, before you do further analysis, you want to check, is the data following a certain curve or are they not following a certain curve? So you can't actually do any further analysis unless you're sure that it is following normal distributions, or if you're fitting another distribution to it, and so on. So here on the histogram, it appears to be slightly skewed, but with the probability plot, it helps us to conclude that the data is normally distributed. So if we fit it into a normal distribution plot, it's showing that it's actually pretty normal. So we can assume that our data is coming from a normal distribution. Any analysis that we will do based on this. Here in this case, the histogram is skewed significantly. As you know, as you can see, this curve is not fitting anymore. And if you look at the probability plot, again, also, you don't see that it's aligned anymore. It's probably coming from two different distributions. You can see that there is one here and maybe there is another one here. But you can tell just from doing the probability plot, again, that any analysis based on normal distribution is not good analysis, because your data basically does not follow normal distribution, because this is what you do actually. Once you go to statistics, you assume that it is following a certain distribution. But in this case, no, any analysis you do with this is not, this is not. So probably you'd like to look for another distribution to do your analysis, or maybe you want to convert it to another distribution, or you could, there are different ways of dealing with this, but this is outside the scope of our discussion here. Another important thing is the time series plots. A time series, what it means, very simply, this is time, your x-axis is time, and that's your data points. So here, if you look at the data here, you're plotting this one and this one, you can see that these are coming from two different distributions. And where can you find two different distributions? If you go to a school, for example, and you take the age in a kindergarten school, for example, and you'll see that there are two distributions. Basically, one distribution maybe for the teachers, and another distributions for the kids. So you can't mix them together when you do the analysis. You can't say that the average age in this school is this much, because you're actually looking at two different distributions. So just by looking at a time series plot, it can tell you a lot here. And this plot, for example, as you know, you can see that there is a trend up. So you can actually learn a lot from just looking at the time series plots. Another thing that you would like to look at when you take your data, you want to look at the run charts. Run charts, you just take the data and you say, I want you to give me a run chart. And the data has to be put in sequence according to time. This is the first one, this is the second one, and so on and so forth. So here it will show you if your data has a trends, basically. And the trends, what does a trend mean? It's just fewer runs up and down, because if your data is going up and next time is going up and next time is going up and next time is going up, it's not like coming down and up and down and up. So there are fewer runs, so you can decide. That's how statistics does it. You decide that there is a trend. But on the other side, if no, they're going up and then coming down, going up and then coming down, then that's probably an isolation. So you don't want, before you do the analysis, you don't want trends or isolation or clustering. Clustering is basically a fewer runs around the median. This is your median here, and this is a clustering. So you have one cluster. This is a cluster here. This is another cluster, and so on. But again, the p-value is always your gate. So here, if you look at the p-value, you can see there's only well, here sorry for the poor quality of the slide, but the p-value is more than 0.05. Anytime you see a p-value more than 0.05, this is the normal set point. I think in medicine they use 0.01, but in other application they use 0.05. Anything you see more than 0.05, the p-value, so you say, okay, there's no trend here. This is more than 0.05, so there is no isolation in my data. This is more than 0.05, so there is no mixture. It's only cluster that's there. So that's the way you actually look at the data. It's very important. It gives you, do I have a trend? Do I have isolation? Do I have, because this is all very important. You need to look for causes of why things are going like this. Another very important tool when you do your data analysis is the Perito. And I'm sure many of you have heard Perito, and no Six Sigma yellow belt or green belt holder not know. You should know what Perito is. Perito is a method to classify failures or anything actually, or defects, in terms of relative significance, and sometimes referred to the 80-20 rules. They call it 80-20, and I'm sure many of you are familiar with, have heard the 80-20 rules. And sometimes it's called the ABC analysis. A is the most significant, and B less significant, and C, and so forth. So this is another way to call it. And Pareto principle suggests that 80% of the consequences come from basically 20% of the causes. So if you just look at 20% of the causes, you are covering 80% of the consequences. Pareto is a European scientist from the 18th century, and he noticed that 80% of England's wealth is with 20% of the population, and to his surprise, also that was all the same all over Europe. I think 80-20 is no more 80-20. It's probably 95-5% now, but that's where it's coming from. This is a Pareto chart from Minitab, and as you can see, the most significant are plotted first. So we counted 150 seal failure. This is mechanical seal failures. We counted 43 bearing failures, and all the others were 21. So 150 over the total, that's 70% of all the failures. The bearings were 20%, but the cumulative here, and this is what we are after. So this one is 70%. If you add to it bearings, you will get 90%. So just by looking only at mechanical seal and bearing problems, you don't need to look at all problems with your equipment. Just look at these two things, and then you will be covering 90% of your problems, because this is 70% and this one is 20%. So the total is 90%, and it helps you where to focus. You don't want to focus on maybe, I don't know, maybe 20 other problems that are occurring only once, and maybe even their significance is not very important, very significant, and so on. So this is where Pareto is useful. It helps you focus on what problems you want to focus more first. So here are features. This is the cumulative. At the end, it ends up with 100. It's the same, just plotting these numbers there. So 70% is that's the 70 here. That's the percentage here. So 70% of mechanical seal, 90% maybe is seals and bearing, and of course all of them are contribute to 100%. An important thing, and also very likely, that, well, I don't want to say exams, but if you're a green belt, then you should have at least known what a box plot is. A box plot is basically just a plot of the data. You have a data, it tells you this is a box. It's called box plot because it's a box. It's a plot of a box. It starts from the first quartile of the data and ends up at the third quartile. Of course, the middle is the median, as we said, first quartile, second quartile, which is the median. So this is the middle. So this is a point. So this is 2, 3, 4. So your median is here, maybe at 3.6 or something. And this is your first quartile, and this is your third quartile, and this is your average. Your average, it doesn't, sometimes it's the same as the median, but it doesn't have to be the same as the median. So that's called a box plot. Then you go to a whisker, something called a whisker. A whisker is basically 1.5 the distance of the box. If the box from here to here, that's the distance from here to here. You multiply this distance is 1.5. Anything actually beyond the whisker, whether this way or this way, they are called outliers. So this is another way of looking where your outliers. You're collecting data from your lab, from your taking measurement from whatever survey. You want to look at the data. You want to see which one are outliers and which one are not outliers. But you don't throw outliers. You don't say this is an outlier, I'm going to throw it away. No, you need to investigate. Why is it? Just like we said, somebody that day he came very late. It's an outlier. It's not normal for him, but we need to investigate because that can be a cause of a problem. Okay, we need to investigate why it happened. This is just another way of plotting the box plot. Here it is plotted horizontally. This way, here it is plotted vertically. So it's the same thing. This is the length of the plot of the box. This is 1.5 times. So these are the whiskers. Any data point that's outside is an outlier. Here we're comparing three services. This is a mail service. There's an express. There is normal, and there is an overnight service. So we're checking the weight. This is the y-axis is the weight, and we can see that this guy is actually different than this guy here. So it's clear. But this one and this one, we don't know. Yes, there is difference, but we're not sure because they're overlapping. We can't be very sure that they are different. So maybe you know, the sample that we took, it just happened to be like this. So this is important. Another thing, another tool when you look at the data is the scatter plots. The scatter plots is very important, and basically you're here in a scatter plot, you're plotting one variable against another variable, and most likely these are, you know, they can be output and input, but they can also be input with an input. You know, just like here, this one is called a matrix plot, which is the same as a scatter plot, but you're plotting all the variables. So for example here, if it's a telephone service, answering service, so the answer time is is inversely proportional with the number of personnel. So the more personnel you have, of course, the shorter time you're going to get answers. So this makes sense. The number of personnel with the incoming calls per hour, there is no relation because this has nothing to do with this. There's no correlation. But if we look at this one here, for example, so the time per call with the number of personnel, yes, the time per call will actually, so we know the relation between the various inputs, how they are related to each other. So now we want to go from graphical results, even in the data now, even in the data door, we looked only at the graphical. Now we want to move from graphical results to statistical significance. And in the graphical results, for example, if you look at the process A, the box plot, you can see that it has a lower average. See, this is the median. This is the third quartile. This is first quartile. But if you look at this sample A and sample B, you can actually see that this guy has lower average, but it has more variation. Look, the difference between first quartile and second quartile than this one here. So lower average and more variation. But when we make a conclusion like this, how confident are we? You know, this is only graphical. We're looking at a graph. So how are we sure that this did not happen by chance? So maybe there's a pure chance here. So maybe they have the same mean and standard deviation, and just happened we got a few high results, and that's what happened here. So to be sure, what we need to do, we need advanced statistical tool and to check the significance. And this is where we now go into deeper statistics. So bear with me for the next 20 minutes because it's going to be a little bit heavier. Okay. Good. So let's look at something called confidence interval. which is very important. And that's actually, if you understand this, then you are understanding. You will be understanding statistics, inferential statistics. You know, we do descriptive statistics, and we have inferential statistics. But let's look at this. So this is a normal distribution. Okay, let's say that you take a sample and you say, okay, I want to know the average age of the university students and in a particular university. So you can't go to all of them. So you're going to take a sample, and let's say you take a sample and you get the average of that sample. Okay, let's say you take the sample, it's 100 random samples, you get 100 people. You take their average and you say, okay, the average is whatever, it's a value here, and let's say it's 20 years. Now, how confident that this 20 years is the real average for the whole school? Can you swear in the Quran, okay, that this is the age, this is the average age for the whole population? No, this is only the average of the sample that you took. Now, how confident am I in this average that I took? This all depends on the standard deviation or a standard error, to be more accurate, because standard error has to do with the sample size as well. Okay, so it's all depends on the standard deviation, and this is how we calculate it. We say, well, the average that I get for the sample is 20 years, but I am what? I am 68% confident that the population mean is only one standard deviation below that number or one standard deviation above that number. Let's say that the standard deviation is 1 year, for example, and the average is 20 years. I say it's only a sample, but I'm confident. What? I'm 68% confident. That's what 68% means here. I'm 68% confident that the population mean is within 19 and 21. That's the only thing I can draw. I can't say they're exactly 20 years. No. If you want me to be more confident, I tell you that I'm 95.5 confident that the average age of the whole school is between 18 and 22, which is standard deviations or standard errors below and standard errors above. Or if you want me to be 99.73, I can now maybe swear, okay, that they are between 17 and 23. This is what the 3 standard deviation is. That's the whole story about inferential statistics. If you understand this concept, then you are, what, 90 steps ahead, you know, in understanding this. So basically, you have a z value or a key value or other values, but here they call it z-score, okay? And it depends on the number of standard deviation or standard errors away from the mean. If you are 1, then you're 68% confident. If you are 2, then you're 95% confident. Like in this case, you know, like what? It's 1.64 here. If you're 2, like you're 98%. That's if it's one-sided. Of course, there is one-sided and two-sided. I don't want to confuse you here, but that's what it means. If you ignore this part and you look only at this table, you say that I am 98% confident that my data will be between 2 standard deviation below and 2 standard deviation above. I am 95% confident that my data will be 1.46%. Sorry, 64%, 1.64 standard deviations below and 1.64 standard deviation. This is just how many standard deviations below and above the mean to be 95% confident. That's what it means. Think about it, you know, read it again, and that's basically what it means. So that's what confidence interval. And it's very important. You take data, you want to be, how confident are you in your conclusion? You're drawing a conclusion on a population based on a sample. How confident are you in this? Now we go to hypothesis testing. Hypothesis testing is nothing but what we just said here. It is very related to confidence interval. So hypothesis testing, and if you're going to do green belt or black belt, then you will get questions about hypothesis testing, and most of the questions are general, conceptual. There will not be calculations, just do calculations on it. No, they will actually see if you're actually understanding the meaning of hypothesis testing. Hypothesis طبعا in Arabic الفرضية يعني اختبار الفرضية. Hypothesis testing is estimating the risk of wrong decisions. How much confident I am, so how much risk do I have? How much wrong decision am I making? And it's a tool for comparing population parameters that is inferred from the sample. Just like we said before, you take a sample, you want to say how confident I am, or how much risk do I have if I give this estimate, okay? Then it tells you how much risk there is. So that's what hypothesis testing. Hypothesis testing, there is a null hypothesis. A null hypothesis is like the beginning hypothesis. The null hypothesis, which is the starting hypothesis, you assume that there is no difference. Okay? You can and to reject the null hypothesis, you have to prove that there is a difference. So you take a mean, and you say this mean is the same as another, is different than another historical value, for example. Let's say you do improvement in something. You say, oh, now I have improved and my data is different than it was in the past. The hypothesis testing, the null hypothesis is that there is no change. And if you want to say that there is change, you have to prove to me that there is a change. And so the null hypothesis is always the equality. They're equal. So that's what the null hypothesis. Let's look at this example here and try to understand hypothesis testing from this example. Let's say that the lube oil drain temperature value, it doesn't matter, lube oil, patient temperature, whatever, but the temperature value has an average of 150 degrees Fahrenheit. And now we take a new sample, and let's say the sample is 16 readings, and we calculate a new average of 160 with a standard deviation of 10 degrees. So that we know how to calculate the average, and we know how to calculate the standard deviation. So we calculated 160 as the average and 10 degrees as the standard deviation. And now the question is, we were at 95% confident. Would you say that there is a difference? Can you say that, yeah, it was 150. Now I'm taking new data and I'm seeing it to be 160. Can you say with confidence, with 95% confidence, that there is a change? This is the way you do it. You do hypothesis testing. So the null hypothesis, المبدئية, is the means are the same. They're equal. There is no change. They're just a different, just random. You just took a sample. Okay. So you assume the first assumption is that there is no difference. So you say no difference. The alternative hypothesis is they are different. So you have to prove. Okay. This is the way to do it. Very simple. First of all, you calculate the Z value of 95% confidence, and you just look it up from tables, like the table that we showed you here. Just like a table like this one. Of course, they're different if it's a T distribution, if it's a Z distribution, and so on. But they're lookup tables anyway, and the software will look it up for you and will do the whole thing for you. But this is just to illustrate the concept. So let's say that for 95% confidence, you need to be at least 1.64 standard errors away from your mean. Let's say it has to be really different. How different? You have to go further for at least not one standard error away, but at least we need one, almost two here, 1.64, almost two standard errors away. So that's what it is. So you calculate your standard error, which is very simple as we did. You take your standard deviation, you divide it by the square root of your sample size, which is 16 data points, and you get 2.5. So that's your standard error. Now you say, I'm confident that the new average that I got is what? Is the mean that I got plus or minus 1.64 times 2.5. So this is similar. It's between this minus this value and plus this value. So you calculate 2.5 times 1.64, you subtract it from 160, you get a value which is 156, and the same value you add it to 160 and you get 164. So what are we saying here? You're saying I am 95% confident that the new process has a range, basically, or a confidence interval between 156 and 164. This means here that you actually can reject the null hypothesis. Why? Because, yeah, I can say that it's different now. Because it used to be 150. Now I am confident that it is between 156 and 164. It cannot be lower than 156 because of the data that I just calculated. So I am now confident. I'm saying this is my confidence. I'm confident with this sample size, with this standard deviation, with this mean, that my data is actually between 156 and 164. So yes, I have changed. The average temperature is not the same. The average temperature has changed. And now you can actually draw a conclusion. That's what it is. That's all there is into it. Okay. So you didn't need to do this calculation. If you have a software, the software will do all the calculation. All you need to do.
Doctor, excuse me.
Yeah.
Excuse me. If we go back to the slide.
Who's this? Who's this? Your names are not showing with me.
This is Muwaffaq.
Muwaffaq.
Yes, Doctor. Here we are talking about temperature and Fahrenheit. And down its months. Is it?
Oh yeah, I'm really sorry. It is Fahrenheit. It's not months. I'm really sorry. My mistake.
Okay.
It is. Yes. Thank you. Maybe. Why don't you? You'll be my assistant in finding all the problems with my slides. But
I
you
will be very happy.
Right. They are not months. They are Fahrenheit. Yes.
Yes.
Well, that makes me happy because I know people are still following me. You know, they're not all finished with my lecture. There's still people following. Okay, but again, you don't need to do this calculation. If you have a software, the software will do it for you. But you need to understand what's in the software. That's why we show you this. Okay, so if you have summarized data with a sample size of 16. And a mean of 160, and the standard deviation of 10, and this is your hypothesized mean, the past, then you hit OK, and it will give you, this is the analysis here. As simple as this. It will tell you that, that's your standard error of the mean, 2.5, as we calculated it. And this is your 95% confidence interval, and it's your data should be between 154 and maybe 165. Okay, that's your confidence interval. So if historically it was 150, you are different. And how much the p-value is also very important. Always look for the p-value. The p-value is if p is low, the null must go. And if P is high, the null is our guy. So if P is low, which is lower than 0.05, this is the setting that we set it. This is 0.001. So it's lower than 0.05. So it is low. So the equality must go. The null hypothesis must go. And we say that this sample is different than the historical mean, basically. That's the way things. Here, if you don't have summarized data, you don't need to calculate it in a different software. Just give it the data. You put normally columns here. You put it the column, what column? It will actually calculate for you the mean, the standard deviation, and it will do this. So either you enter it as a summarized data, like in this example, or you enter it and you can enter the raw data and it will do the calculation for you. There is the one sample T. I'll finish these two things about hypothesis testing, and then we'll close it for today if that's fine with you. We're coming close to 10 o'clock, but maybe it's a good idea since we're talking about this. We'll finish it. So that's if you have data that you want to compare to a historical mean. But if you have two samples and you want to see, is this sample different than this sample? So this sample has a mean and a standard deviation, and the other sample has a mean and a standard deviation, and you want to compare the two samples together. So what you use a two-sample t-test. And it is similar to that one. You just calculate the confidence interval of the first sample, you calculate the confidence interval of the second sample, and if they don't overlap, let's say the first interval of the first sample is coming, say, okay, I'm 95% confident that group A is between 15 and 18. And I am 95% also confident that group B are between 20 and 25. Since these two ranges do not overlap with each other, they're far away, then you say, okay, I can reject the null hypothesis, and I say that these are coming from two different distributions. But if they touch, so they overlap, one of them, let's say, between 18 and 20, and one between 19 and 21, so there is one overlap here, 19 and 20. So you say, no, I cannot reject the null hypothesis. So I don't have enough evidence that they are different. They can be different, but I do not have enough evidence that they are different. The last thing here is the pair test, pair sample. Sometimes if you compare two populations, let's say we're comparing men and women, ages of men and women. If you compare men and women, you will not see that men are older than women on average, because these people live long, these people live long, these people die young, some people die young here. But if we want to compare husband and wife, okay, or normally wives are younger than their husbands, right? So how do we compare, or shorter than their husbands? So if we just mix the data together, we compare group A, all the women with all the men, we probably, for age, we will not see a difference. Maybe for height, we will see a difference, but for age, maybe we will not see a difference. But if we pair the test, we do a pair test, each husband with his wife, yes, we will see that men are older than women, on average, and as a general rule, you know. So that's basically what a pair. This is why some shoes manufacturing, if they want to test the quality of the shoes, if they give it to children, different children, some children are hyperactive, some children are very quiet, and so on. So what they do, they give the same shoes, the same, you know, they give the same person, the same child. They give him one shoes from brand A, and the left is from brand B. So now it's the same person actually using the same shoes, so and they're actually tackling this difference. But the analysis is the same. It's the same concept. You'll use the software. You enter the data. You put the data for group 1 in column 1. You put the other one in group 2. You just do paired analysis or one sample T or whatever. You just call that analysis, and it will give you the analysis. And all you need is just to look at the confidence interval and the p-value. These are the two things that you look at. Now you have confidence that product A is better than product A, method A is better than method B, and so on and so forth. So you can actually make conclusions or inferences based on statistical data. I think we'll stop here today. Any question? Sorry for the online situation, because if we do this face to face, I can see who has a question really in his face, even if he's shy. But in this case here, I cannot do much. I hope that I'm getting the message across.
الله يعطيك العافية دكتور ما قصرت. It's a really great new concepts in quality and a lot of statistics. I like statistics, so it's an area I feel very comfortable in. Thank you so much. It's really great so far. الله يعطيك العافية.
I'm very happy to hear that. Any other comment, any other questions, any other closing things before we close for today?
Any suggested software to use it?
The most common software,
this calculations.
Yeah, the most popular software is Minitab, and I'm giving you most of the example from Minitab. There is Sigma XL. Sigma XL is also another good software. And to be honest, many of these things can be done even in Excel. Excel is very powerful if you can look for but there are Minitab and Sigma XL are more specialized. But even Excel, sometimes some of these functions are actually in Excel, and you can find them in Excel. Please try to at least create a project charter. It will be good. It's nothing like working in a real problem. Take a problem at work, even if you can go to your management and convince them to give you time, fine. If not, take a problem and follow these steps, these tools. Take them one by one. Try to learn. It's a method also. It's a good method for learning your business. Honestly, this is it tells you a lot about your business. Just go and use them. You'll find out that you thought that you know your business. Now you know your business better. Just take data and collect them, plot them, try them, use them, and you'll see. Just use these tools. You will learn a lot. You'll find yourself that you need to investigate more information. You need to. So if you can do it in a group with the management support, that's the ideal thing. But if you can, then try them. They're good tools. Any other question? Dr. Fayyaz, Dr. Hawra, Hussam, Dr. Suleiman, we want anything?
No, thank you, Doctor. It's clear. Thank you very much.
You're very welcome. Very welcome. Anything? So shall we close it for today? All right. Then I think we're gonna close it for today. So we'll see you tomorrow night at the same time. I will send you the same information. I'll send you the link for the presentation, and I'll send you the link, Zoom link for tomorrow. All right.
Inshallah.
Thank you, Doctor.
Thank you.
Thank you.
Thank you, Doctor.
Thank you very much. Thank you.